Welcome to the answer video of the spherical fungus flake exercise. I will demonstrate to you how to solve this problem. So the first thing you should do is to make a sketch of the situation. As already said, the flake will be considered as a sphere, and thus we will use spherical coordinates. We have to imagine the problem in 3 dimensions. At the center of the sphere, the radius r is 0, and the total radius of the flake we will call the big R. The oxygen concentration on the outside of the sphere is C star, and oxygen flows from the outside into the sphere. Now we will define our control volume. We will set up a balance over the distances r and r plus dr, which is an infinitely thin layer on the inside of the sphere. In other words, the layer is dr thick. So you can see the inner circle lies at a distance r from the center, and the outer circle, striped circle, lies at a distance r plus dr. You can't see it very well, so I'm making a zoom of the situation. So you can see the first line is at distance r, the second line at distance r plus dr, and the distance between the 2 lines is dr. And you can see that the oxygen is moving from the outside in. Since my sketch is not very well, I pasted in another version on top of it. Now we will set up a mass balance over r and r plus dr. As we know, a balance always has the form of accumulation equals input minus output plus a production term. Now we assume the steady state, which means that the accumulation will be 0. And the input and the output terms are diffusion terms, so they are according to Fick's law. The area multiplied by the diffusion flux, which is the diffusion coefficient times the spatial derivative of the concentration. In other words, dc divided by dr. Here I used immediately, instead of the area, 4 pi times r squared, which is the area of a sphere. The production term will be negative as the oxygen is consumed throughout the reaction. It is a 0th order reaction, so it will be the reaction constant Kr multiplied by the area multiplied by dr. So to sum it all up, 0 is the input term minus the output term plus the reaction term. So yeah, this is your mass balance. So now, in this mass balance, I will combine the 2 diffusion terms on the right hand side of the equality sign into the derivative form. So basically, the r squared and dc over dr are taken into the first derivative. Next, you can put the production term on the other side of the equality sign. From here, you can integrate. On the left side, you can integrate the derivative of r squared times dc over dr, which will then become r squared multiplied by dc over dr. And on the right hand side, you integrate r squared times dr, which will become r cubed divided by 3. The constant that you can add, is easily calculated if you consider the fact that the center of the sphere, the concentration, is constant. So alpha will be 0. And now you will see that you can easily divide by r squared. So the next step is to isolate dc, which means you take everything from the left hand side to the right except for the dc. Now you can integrate on both sides. Remember the border conditions. You start the integration at a radius r inside the flake, and you move outward towards the outside of the flake, so where the radius is big R. And at the points R where you start, the concentration is C function of R, and at the outside it is C star. Now if you integrate this, integration of R times dr will give R squared divided by 2. So if you fill that in for all the border conditions, you find this expression. Now isolating for CR, you get C star minus the reaction constant divided by 6 times the diffusion coefficient times big R squared minus small r squared. So this is your concentration profile. Now to solve the question numerically, the condition imposed at the beginning of the exercise was that the center should receive oxygen at all times. So C at point 0 should always be larger than 0. So this term should always be larger than 0. So you have the maximum radius of the flake is the square root of C star times 6 times the diffusion coefficient divided by the reaction constant. Now if you fill in all the values for the concentration at the surface, for the diffusion coefficient and the reaction constant, don't forget to check the units, it's very important. You can see here you can cross out the moles, you can cross out seconds, you can cross out meters cube, and you'll be left with meters square, which square root gives you meters. So this gives 5 millimeters. And we were asked to calculate the maximum diameter, not the maximum radius. So we just multiply this by 2. And there you go. You end up with 1 centimeter. Now for the next question, for the second part of the exercise, we have to fill in different values. We know that the radius is 0.15 centimeters and that the total radius of the flake is the maximum radius, which we found in the first part. Now we go back to the equation we found for the concentration in function of the radius. So we fill in all of these values just like before. Remember to put that into meters, even though the values were given in centimeters. Now remember to check all of your units. You should end up with moles per cubic meter. So you can see the final answer is 0.027 moles per cubic meter. So this is it. Thank you for watching the video and good luck with the rest of the exercises.